Hi, guys. Hey guys doing? We'll just give it a second for other people to show up. I I want to talk about the quiz that I just graded. I posted grades and I posted the quiz solutions on Tuesday night, I think. I want to go over the quiz. I know you guys can just take a look at the solutions, but there were some repeated errors coming up again and again. People having sort of different conceptual ideas about exactly what needs to happen. So I want to make sure that we get this kind of nailed down here. So you guys can find the quiz solutions up on the modules page where the quiz was posted. Okay, but like I said, I want to go over it because your rubric will be there, the quiz solutions will be there, but let's talk about it. Okay, so this is quiz for chapter 2.9 and 3.3. Okay, and then don't forget, today we have a quiz also that opens up at noon. It'll be on chapter 3.5. Okay, so question 1, what we're given is we're given a function x squared e to the x plus 1 on the interval -4 to 4. And we're asked to come up with 2 things. You have to read the question. It wasn't an A, part B. It was all kind of meshed in, right? These are set up like final exam type questions, okay? So the first question is, where are the local max and local min points? Okay, so local max and local min, I have to do, the process is going to be different than what I took for global max, global min. Okay, so local max, local min, the process is I take my first derivative, I set it equal to 0, and I solve for x. This gives me the critical points. Okay, my critical points, now I need to do, on those critical points, I have to do a first derivative test or a second derivative test to show local extrema. Okay, so for local extrema, you have to do first derivative test or second derivative test. Also, be careful. What I saw again was, I think, I don't know if some of you guys had AP Calc perhaps, and you're accustomed to drawing this number line with the critical points and then the arrows and whatever. That is not enough for full credit, okay, to show your work. It helps if you write first derivative test or second derivative test. You have to tell people what you're testing it on, okay, and you have to show values that you're plugging in. So my first derivative test, I'm going to test on my first derivative some value less than my critical point, right? And I'm going to get, is it positive or negative? My first derivative test is then some value greater than my critical point. And I'm going to get, like, this is positive, this is negative. I'm looking for a sign change around my critical point. So if it's positive heading towards it and it's negative afterwards, that means my function's increasing to decreasing. That means I'm dealing with a max, right? So to do this, right? Or, hang on a sec. Or I do the second derivative test on the critical point, and I get positive or negative, depending, right? One is concave up, one's concave down. If it's concave up, I'm dealing with a min. If it's concave down, I'm dealing with a max. Both of these are totally fine, but you have to specify what it is you're doing, and you have to do this. If you do a number line, right, or like, especially like I'm seeing like tables of just numbers, so I have no idea what function you've plugged things into. Okay, if you just give me like a table with numbers and values, and then you do arrows and stuff like that, I have no idea what function you're plugging things into. Okay, so make sure you're very clear. And I say this honestly because when we grade the final exams, I have seen people do those number lines with the arrows and whatever, and they don't get credit for it because it isn't clear. Are you doing first derivative test, second derivative test? What is it that you're actually testing? Are you testing on the function? I mean, what's happening? So those are not enough. Okay, so be very, very careful. You don't want to lose points. It's bad enough you lose points on a quiz, right? We dropped the 2 lowest quiz scores. This isn't going to kill your grade so much, but on the final exam's worth a lot, and you only have like a handful of questions. Okay, so don't blow it on things where you can build up points. We're going to go through and actually work it through, but I just want to talk about this. So local max, local min, you're doing a first derivative test or second derivative test around or on our critical points, okay? For global extrema on a closed interval, which is what we have here, right? So global extrema, I'm checking my function on the end points, endpoint 1, function endpoint 2, and I check it on the critical points. Sorry, I have a sore throat today. So I check it here, and I'm actually looking for a value. Here, I'm looking for which one has the greatest value, which one has the smallest value. These are going to tell me my global extrema on a closed interval. Local extrema are just where, like, if I have this wide open interval, where am I getting like little, where's the activity happening? Okay. All right. So process. Now let's actually go through and do it. So on this question, so our derivative, I have to do the product rule, right? Because I've got x squared times e to the x. So I'm going to go first times the derivative of the second plus the second times the derivative of the first. And I have to set that equal to 0 and solve for x. So what I saw, also another mistake that I saw was people subtracted this and then they canceled terms. You cannot do that. We're factoring, we're setting each factor equal to 0, and we're solving for x. Okay, so what I'm going to do is now I'm going to factor. So I've got an e to the x term and I have an x term I can factor out. So I've got an e to the x, and then what do I have left over? X plus 2 equals 0. So I have 3 factors I have to check. E to the x equals 0. Okay, this one actually has no solution. If you look at your graph of e to the x, it's asymptotic to the x-axis, so it has no solution, right? So that's my first one. So x equals 0, right? This factor. Okay, I found one of my critical points. The other one, x plus 2 equals 0, subtract 2. So x equals minus 2. So I found my critical points. They also happen to be within my interval. So critical points, x equals 0, x equals minus 2. Okay, now I need to do a first derivative test or a second derivative test. I did a first derivative test just because I didn't feel like doing a product rule twice. So first derivative test. Okay, so I'm going to check for values around each critical point and see what I get. So I did the first derivative. I chose, so if minus 2 was one of my critical points, I chose a value just slightly less than that. So I chose minus 3. So I plugged that into my first derivative. So I'm going to plug it into here, right? So I'm going to go minus 3 squared e to the minus 3 plus e to the minus 3, 2 times a minus 3. Right, and I got some value. It doesn't matter what the value is, but it matters the sign. So that was positive, was a positive value. I'm going to choose a value on the other side of minus 2. So I chose f prime, I chose minus 1. So I'm going to do the same thing. So minus 1 squared e to the minus 1 plus e to the minus 1, 2 times minus 1. And then this one, I got a negative. Okay, so look, I've got a sign change around my minus 2. Okay, so I've got a positive, then a negative on my first derivative. So at minus 2, right, I've got this positive and then a negative. That means, right, we're dealing with, x equals minus 2 is a local max. Write it out. You have to spell it out. This is what you're being asked for. Okay, let's do it for the other one. So minus 1 will also help us with x equals 0. So I just need another point on the other side of 0. So I'm going to check. This is going to be, let's see, this is going to be 1 squared e to the 1 times 2 times 1, right? We're plugging it in. So on this one, I got, this was a positive number. So at 0, right, we're going negative to positive. So that means we're dealing with x equals 0 is a local min. This is a local min. Okay, it's not a global, it's a local min. Right? Our first derivative test, second derivative test are going to show us local extrema. Okay. That was the first part. Now they said which of these are global. No, with the global extrema, I have to also check the endpoints. Okay. So which are global? All right. So I had to do the endpoint check. Endpoint check, and I have to do the critical point check. And I'm checking them on the function now. So on my function, I plug it in. So I plug in, I'm actually looking for values. So I take my critical points and I plug it in. This is 0 squared plus 0 squared times e to the 0 plus 1. That's just going to give me 1. Minus 2, I got 1.5. F of minus 4, I got 1.29. F of positive 4, these are my endpoints, right? Okay, 874.5. Okay, so on this, I'm looking for the smallest value and I'm looking for the biggest value, right? So I'm going to say x equals 0 is a global min. X equals positive 4 is a global max. That's on this interval, right? If I didn't have it on the interval, we'd be dealing with, minus infinity to positive infinity, okay, or minus infinity 1. But anyway, so we're dealing here, okay, with our values, okay? So global versus local. All right, question 2 is another source of confusion. So our position function as a function of time. I have my x coordinate 3t, e to the 6t, that's my y coordinate, and my z 2 sine of t. So I can think of x of t is 3 to the 3t, y of t equals e to the 6t, and z of t equals minus 2 sine of t. I've got 3 components, okay, that makes it an x, y, z. All right, so now our average velocity, you have to be super careful because average velocity is change in position all over change in time, right? So this is delta p over delta t. So what I'm going to do is I'm going to say the p, we're given 2 different time t0 and time 3 pi. It doesn't matter what order, just keep it consistent top and bottom. I did 3 pi minus p of 0 all over 3 pi minus 0. Okay, so I'm looking here. Don't take the derivative, okay, because we're not looking for instantaneous velocity. We're looking for an average velocity. Okay, so now I'm going to break it up into my components. So my x component of my velocity, this is 3t. So I'm going to go 3 times 3 pi minus 3 times 0 all over 3 pi minus 0. So this is 9 pi minus 0 all over 3 pi. Pi's cancel, 3's divide, I get 3. My y component, e to the 6t. So e to the 6 times 3 pi minus e to the 6 times 0 all over 3 pi minus 0. So e to the 6 times 3 pi, that's e to the 18 pi. E to the 0 is 1. That's all over 3 pi. Some of you guys multiplied all this through, like you gave me, something times 10 to the whatever. Leave it in terms of e, leave it in terms of pi. I didn't take off points if you multiplied it all the way out, but we typically tend to look for answers in terms of e or in terms of pi. So don't worry, unless we tell you specifically to give us a decimal number, leave it in terms of e or pi. Our z component, right? So I'm going to look at minus 2 sine of 3 pi minus 2 sine of 0 all over 3 pi minus 0. All right, let's think. So sine of 0, this is 0. So let's think about 3 pi, right? So 3 pi, right? So here's 0, here's pi, here's 2 pi, here's 3 pi. So my odd pi's are the same thing. They're right here. So my sine of 3 pi is also 0. So this is equal to 0. I accepted this as an answer but technically speaking, I needed to put this back into a vector. So 3 e to the 18 pi minus 1 all over 3 pi and 0, our average velocity. Be careful, don't take the derivative and then divide it by the average time, right? We're taking the change in position over the change in time from those 2 time points, okay? All right, part B was dy dx. So that means I need the derivative of y with respect to x. So I'm going to go back up, see these equations here, right? So I've got my x of t and I've got my y of t. So I only need those top 2 because I didn't ask for dy dz, it just said dy dx. So let's remember, so x is equal to 3t, and then y is equal to e to the 6t. Now, this derivative here is all just in terms of x's and y's. There's no t's. So I need to solve for t equals x over 3. Then I'm going to take that t and I'm going to plug it into here, right? So then I'm going to get y equals e to the 6 times x over 3, which is equal to e to the 2x is y. Now I take that derivative, right? So now I can go y prime, which is equal to dy dx is equal to, well, I got to repeat my exponent, and then I got to do the chain rule, 2e to the 2x. Some of you guys did like dy dt over dx dt, and then you divided through, but I think you made some mistakes with your cleanup stuff. That you should be getting, everything should be just in terms of x and y. Okay, so be very careful on that. Okay. To the optimization question 2, question 3. So most of you guys kind of had the general idea, but some of the answers were kind of all over the page, so I want to make sure that we have it. So we're given a coffee cup, right? It doesn't have a top. And it doesn't have a handle, which is nice. I don't have to figure out that area. Okay, so I've got this. So it just has a radius at the bottom, and of course it has a height. Okay, and we're given the volume is equal to 128 pi cubic centimeters. And we're asked to find what's the radius and what's the height. Okay, so I don't know anything except the volume. Well, I also know that the volume equation is pi r squared times the height. So that's the area of the base times the height. Okay, it gives me the volume. So I'm going to exploit this to solve for one variable in terms of the other, and then I'm going to plug it back in. All right, so I need to break it up in terms, they tell me the cost. I need to minimize the cost, we were told. Okay, so I'm going to minimize the cost. The cost of the base of my cup is different than the cost of the sides, and so I have to add those up differently. Plus I have different geometry on each of these. So let's draw them out. So here's our, so here's the bottom of the cup. It's a circle with a radius, right? And the area of the bottom is equal to pi r squared, right? So the cost of the bottom is equal to, they said it was 2 cents. I converted it to dollars. It doesn't matter. You can leave it in terms of cents. You get the same answer at the end. It doesn't matter. I don't know, I just converted it to dollars. So the cost of the bottom. So now what the total cost, so the cost of the bottom is going to be the area, pi r squared, times the cost per cubic square centimeter. Okay. Piece 1. Piece 2 is our side. Right? If I cut this and I unwrap it, that's what they call unroll it or unwrap it, right? It's like a soup label. It's surprising. It's just a rectangle. So the side is a rectangle. One side is the height, and this side here is the circumference of our circle, right? Because it has to wrap around. Okay, so the area is just base times height. So 2 pi r times height. Okay, and then the cost of the side, they told us was, I think it was 0.01. I like I said, I converted it to $1. Was 1 cent. You could have kept it in cents. It doesn't matter. Okay, so let's talk about cost of the side is going to be the area times that cost. So 2 pi r h times 0.01. Okay. So our total cost is going to be adding those together. Total cost is cost of the bottom plus cost of the side, which is going to be equal to pi r squared times 0.02 plus 2 pi r h times 0.01. Okay. I have things in terms of r and h, but I just want one variable. So I'm going to go back to my volume equation. Remember this thing here, and I'm going to solve for one in terms of the other. So remember, our volume was equal to 128 pi. I'm not going about the units. Is equal to pi r squared h. It doesn't matter which one you solve for. If you want to solve r equals, you're going to have r equals some square root of something. Okay, I did it in terms of h just because whatever. So I solved for h. So I got h was equal to 128 over r squared. The pi's cancel. Remember this because you're going to need it later. Once you solve for r, you're going to use it to figure out what h is, right? All right, so let's plug it in to get the total cost. I'm going to plug that in to here. Okay, so my total cost is going to be 0.02 pi r squared plus, I'm going to multiply this 2 times 0.01, 0.02 pi times r times h, 128 over r squared. Okay, so I plugged in that h right into here in this equation. So my cost equation, I'm going to multiply it all the way out, 0.02 pi r squared plus, right, I multiply all these things through and I got 2.56 pi all over r. This is the equation that we need to optimize. We want to minimize it, right? We want to find the min, which just means we're going to have to find the radius, which is going to give us a minimum. Because we were asked to minimize our cost, right? You know, typically don't want to maximize your cost on an item. Okay, so I need to take the derivative. So cost derivative, and I'm going to set that equal to 0. So I'm going to take my derivative. This is with respect to r. R is my variable, right? So I'm going to get 0.02 times 2 times pi times r. Take this derivative here. I'm going to get minus 2.56 pi all over r squared. I got it equal to 0. I do a bunch of algebra, right? You're going to get r cubed equals 64. I take the cube root. I'm going to get r is equal to 4. I have to check to make sure this is a minimum first. Okay, which means you can either do the first derivative test or the second derivative test. I think I did the second derivative test. Right, so I took my second derivative, and it's up to you. It doesn't matter which one you choose, you know, just do it correctly. So I took my second derivative. So I'm going to go 0.04 times pi, right? Because I'm taking this derivative here, plus 5.12 pi all over r cubed. And now if I plug in my 0.04 pi plus 5.12 pi all over 4 cubed, I get a positive number. Okay, so positive number means it's concave up, right? Which means therefore r equals 4 is a minimum. Okay, we have to show that check. We have to prove that it's optimal. I can't just take the derivative and say, there you go. You have to show that it's a minimum or a maximum, depending on what's being asked of the equation. Okay, so now from here I can solve for the height. So the height, I plug it into 128 over 4 squared. I'm going to get the height is equal to 8. Right, so I got r equals 4, h equals 8. But you have to go through, you have to show the minimum part. I don't know, some of you guys had, some of your answers were, I couldn't quite figure out like how you got your answers, but anyway, the solutions are up online right now, but I wanted to talk about it, talk it through, because I saw similar types of mistakes coming up again and again. Okay, guys, so take a look for that. That's on our modules page. You'll need that to study for the final exam. Okay, so with that said, we're going to start chapter, it's officially 4.2. but it's also chapter 1.1 in our integral calculus book. So make sure you've got a copy of that second textbook, okay, that you're working from. So this is, I'll call it chapter 1.1. This is from our integral calc book. It's also 4.2 from our differential calc book. There's a little bit of overlap. Okay, you guys should have the homework assignments because I published them, right? But it'll be helpful for you to see. Sometimes our book will go through proofs that I'm not going through in class. I tend to talk about to prepare you for the final exams and to give you the steps and the tools necessary to work through these things. But the proofs and everything and sort of like a detailed discussion of stuff, okay, and kind of more conversational or whatever is inside the book. Also the book, if you have a PDF of it, there's like a little arrow at the beginning of each chapter. You can click on that and it'll take you to a YouTube page where Professor Massey, you know, talks all about the stuff that's in the book. Okay, so we're in the next book now, basically. And you'll see on the homework, it'll say chapter 1.1, but like in the actual PDF, it'll be _ integral calculus. All right, so this chapter is anti-differentiation. So we spent the whole semester talking about derivatives, right? And now we're edging more towards calculus 2, which is, I need to do the other side of that coin, which is to take the antiderivative. Okay, so I need to think about what is a derivative, what is its antiderivative, how do they work together, what are they, right? What's their relationship, and then what does it mean? We're going to spend a lot of time. We're going to start edging into it now this semester, and then we're going to get into it a lot in Calc 2. We're going to talk about antiderivatives and integrals and what do they represent, what can we do with them. Okay, so let's go ahead and get started. All right, so some notation. So I've got a little f of x dx. Okay, what this means when I read this, right, this says this is the antiderivative of f of x with respect to x. And this dx tells me which variable I'm integrating with respect to, okay? It's like when I take the derivative, I need to know which variable I'm taking the derivative with respect to, okay? I have to know, and that also becomes important, especially in like Calc 3 and beyond, where you're gonna have multiple variables that you're gonna be integrating across. So you're gonna do multiple integrals all at once. And you need to know which variable you're working with at a given time, okay? So it's important to see. All right, let's just talk if there are no bounds, right? So that I see there's like nothing here and there's nothing here. If there are no bounds on my integral, then we're dealing with an indefinite integral. And we're going to have our solution will always have a plus c because it's our general solution has a constant term that we need to take into account. If I have bounds, right? So this is a and b. These are my bounds. We're talking about a definite integral. There's no plus c. It's a number. We're going to talk next semester. I think we talk a little bit now about like what this means and what it is we're trying to do. Okay. Okay, so our definition. So if I've got small f of x dx, I get big f of x plus c. So let's talk about what we have, right? So this, right, this is a derivative of big F, right? So if I take the derivative of this function, that's what I'm getting here, okay? This plus c is our general solution. Okay, I need to have the plus c because I don't know, like, because you think about like x squared plus 2, right? I take the derivative of that, the 2 becomes, when I take that derivative, it's just 0. So I don't know, I could have any, right? I could have any possible, you know, this x squared plus 2, it could be x squared plus 3, it could be x squared minus 5. So the plus c helps me say there's a specific solution out there and we need initial values to help us come up with that. But in the meantime, we're just going to put a placeholder here to talk about that. All right. So one of our fundamental theorems of calculus. Okay, one of our fundamental theorems is every continuous function has an antiderivative. Like if I can get the derivative, I can also get the antiderivative, okay? It's a continuous function, which means that this is a derivative. So I've got some function that this could be a derivative of. In this part 2, this is kind of a redundant statement. Basically, the way to get the antiderivative is to take the integral. So let me just write that down. The primary, this is what our book says, the primary step to get the definite integral is to produce an antiderivative. It's kind of a funny statement because antiderivative and integral are like pretty much the same concept, right? I do the integral to get the antiderivative, right? The process of taking the integral will give me an antiderivative is how you can think about it. Right, so we have some properties I want to talk about. All right, so these are a theorem. This is a theorem, but these are like some properties, some basic properties about the antiderivative. So all x in an open interval. You have to specify some parameters first. Interval for which the functions are defined. It's basically like saying we're dealing with an interval and our functions, we can actually get the functions are defined, I can get the antiderivative. All right, so our first property is if I take the integral of 0 times dx, I'm going to get c. Let's go back, let's think. Right, this is my function. If I take this derivative of a constant term, if I take the derivative of 3, for example, I'm going to get 0, right? So that's what we're dealing with here. So this is the derivative of that. So derivative of a constant term is 0. So if I integrate 0, I'm just going to get a constant term. If I take the derivative of 1, right, I'm going to get x plus c. Let's go back and do it again. If I take this derivative, I'm going to get 1 plus 0. So 1, there's my derivative right there. So if I integrate 1, I'm going to get x. Okay, so p is a constant. We're going to say p is not equal to minus 1. We're going to talk about when p is equal to minus 1 in a minute. This is our power rule for integrals. Okay, what this means is I'm going to integrate x to the p dx. P is just a number, 2 or 5 or whatever. My power rule says I increase my exponent by 1, I divide by my new exponent, and then don't forget your plus c. Okay, power rule for integration. Okay, let's deal with when p is equal to minus 1, right? So if p is equal to minus 1, then I'm dealing with x to the minus 1, which is 1 over x, right? So if I go to take the integral of 1 over x dx, what do I get? I get the natural log of the absolute value of x plus c. Okay, if we are taking the natural log, we have to put the absolute value on it, because I don't know what values of x it's going to be, but I have to make sure that it satisfies the domain for my natural log. These domain for natural log is positive inputs, right? So I have to make sure that x is positive. Okay, so we put the absolute value on there until we know otherwise. Okay, so these are some basic things. So some common mistakes when p is equal to minus 1. This happens a lot. So these are mistakes, right? These are things you don't want to do. But let's talk about it because it happens a lot. So the first one is treating p equals -1 as a normal exponent. Okay, what happens if I do that? Let's cruise along. So I'm going to take integral of 1 over x dx, or maybe I've got it like this, right? I'm going to do the power rule. Okay, so I'm going to go x, I'm going to increase by 1, and I'm going to divide by the new, and I'm going to add c. Okay, so, right, this is -1 plus 1, this is equal to x to the 0. So far, so good. X to the 0 is just equal to 1. Oh, whoops, I get a divide by 0 error. No. Okay, so I can't do this, right? But you'll make that mistake. Like, this is a common mistake because people cruise around really quick. You're on the quiz, you're on the final exam, you're on something, you're going really quick, you're not thinking, you're just doing the power rule, and you get this. And then people, I can see it stalls, you know, and their answer on something, it kind of stalls. They don't know what to do now, because how am I supposed to evaluate it if I get this divide by 0? If you get a divide by 0 problem, go back and check it. You know, you could be dealing with this, right? So remember, 1 over x is natural log of x. The other common mistake is, so I got 1 over anything dx equals the natural log of the absolute value of anything plus c. This is no. I can't just take the natural log willy-nilly. I have to evaluate each function for itself. Right, every function that I'm dealing with, I have to look at and evaluate on its own, because each function is individual. So maybe sometimes I can take the natural log, sometimes it's going to be something different. So I have to be very careful and not just plow right through and take the natural log of stuff. It doesn't work that way. You have to evaluate each function. But the good news is we're learning tools for how do we evaluate those things. So you will know how to actually evaluate that stuff as we go along in this class and in Calc 2, and then in Calc 3, you'll be able to learn all of these tools. Okay, so don't just jump in and take the natural log of it, and don't just jump in and do the power rule willy-nilly. You have to think it through and take a step back and figure out, does this make sense? Okay, so I've got my lecture examples, chapter 4.2/1.1, okay, and I'm gonna start working through some examples so we can see. All right, so the first one, this is, sorry, this should be lowercase p. Lowercase p. So we're going to integrate lowercase p to get big P of r. Okay. So we've got an initial value. This initial value is going to help us solve for c. Okay. But let's go through and actually work through our integral and then solve for c at the end. Okay. So I've got equals the integral of radical r, and this is going to be in terms of r. Okay, so now what I like to do always when I do this is I rewrite this as an exponent. So radical, any kind of a root, right, is just an exponent, another way of writing an exponent. So I write it like that. So this I can do the power rule because it's not equal to -1. So I'm going to do the power. So I'm going to go r to the 1/2 plus 1 all over 1/2 plus 1, and then plus c. 1/2 plus 1, 3/2 all over 3/2. Which means it's also true, this is 2/3 r to the 3/2 plus c, and this is p of r. Okay, so it's our general solution. But I can use my initial value to solve for c. Okay, so my initial value, so let's say p of 9 equals -7. So everywhere I see an r in this equation, I'm going to plug in 9. So I'm going to go 2/3 9 to the 3/2 plus c. Now c is my only unknown. All right, so I've got a bunch of things I need to take care of here. So let's do this part first. So 9 to the 3/2, that's like square root of 9 cubed. So square root of 9 is 3. Cubed is going to give me 27. 27 times 2/3, right, that becomes 9. This is 18. So I'm dealing with -7 equals 18 plus c. -18, -18. So I now have c. Once you have c, plug it back into your equation to get a specific solution based on this initial value. Okay. You guys? All right, let's talk about another really important theorem. It's our linearity. This is a theorem. Remember when we did linearity of derivatives, we said f of x plus or minus g of x, and I can take the derivative of f of x, I can take the derivative of g of x, add or subtract them later, right? We can do that with antiderivatives. If I have two things that are being added or subtracted, right? It's just with addition or subtraction. Addition or subtraction. Not multiplication or division. Multiplication and division have their own set of rules we're going to talk about, okay? So this one says, I've got a and b, they're constants, and they're not equal to 0. I mean, if I had them equal to 0, it wouldn't be a domain problem. It would just be boring. I would have 0 times a function, and that's, you know, that kind of defeats the purpose. So I've got a times f of x plus or minus b times g of x dx. And I want to integrate that. Plus or minus means I can do linearity. So I'm going to distribute my integral and my dx. So a times f of x dx plus or minus the integral of b times g of x dx, right? Now I can take these constant terms and bring them through my integral, a times the integral of f of x dx plus or minus b times the integral of g of x dx. Don't forget to multiply through at the end when you get an answer. Well, sometimes people do this nice thing, they bring it out, but then they forget to multiply it at the end, and that's bad. So that's our linearity. Only works with addition and subtraction. Okay. All right, let's do an example. So example 2 is doing linearity. All right, so I've got this example 2. We're going to find this. So I'm subtracting. So I've got this term and that term. So I'm going to 5x cubed dx minus the integral of 7 radical x dx. And I'm going to bring the 5 and the 7 outside of the integral. Minus 7. And I'm going to convert this to an exponent. It helps me think about how I'm going to do the power rule. So now this is going to be 5 times, this is x to the 4th. Remember, I take my exponent, I add 1, the exponent, and then I divide by that new exponent. And I'll do plus c1. Minus, this is 7 times, we just did this, right? X to the 3/2 times 3/2. Divided by 3/2, sorry, plus c2. Okay, so let's just talk for a minute. When I integrated, I have a constant term. When I integrated, I have a constant term. If I do c1 minus c2, c1 plus or minus c2, it's still a constant, right? If it's still a constant, I'm just going to call it c. And I'm going to say plus c because whatever c's value is, right? We said plus c here, but c ended up being negative, right? It doesn't matter. C is just a constant term. So I'll combine this all into one. This is 5/4, x to the 4th, minus, now watch, this is 7 times 2/3. Remember, because it's divided by 3/2. 7 times 2/3 makes it 14/3, x to the 3/2. And then I'm going to say plus c. Don't forget to multiply by the constant terms that you had that you inherited from the original function. Okay. All right, let's talk about trig and exponentials. Okay, so some trig and exponential functions. So when I go to integrate the cosine of x dx, remember, this is a derivative. What is this a derivative of? It's a derivative of sine. Always be thinking about, if I were to take this derivative, c becomes 0. Derivative of sine is cosine. right? So you're thinking derivative, antiderivative, okay? Same thing here. If I go to integrate this sign, right? What's that derivative? Minus cosine. So what's the derivative of cosine is minus the sign times a negative makes it positive, okay? E to the x again is equal to itself plus c. Okay. I'm going to do a general exponential just so you can see, so general. Right, so if I a to the x dx, so here our base is e, here our base is a. This is going to be, I repeat the exponential and I divide by the natural log of the base plus c. We're doing that here, we just don't see it because the natural log of e is equal to 1, right? So right here, okay, remember, if I take this derivative of a to the x is a to the x times ln of a, divided by ln of a just gives me a to the x, okay? So always be thinking, what's this derivative? It should equal to that. Okay, so I'll do inverse trig. This is why you want to kind of have in your mind what the inverse trig functions are, so that we're going to talk about an open interval. -1 to 1. That's for the, our sine function. So if I go to integrate 1 over 1 minus x, oops, sorry, you can't see that, radical dx. So 1 over the square root of 1 minus x squared. This should look familiar, right? This is our inverse sine of x plus c. I'm going to give you the general solution. Our book, I think, doesn't go into a whole lot, although you're expected to know it. So the general, it's going to look like 1 over 1 minus a squared minus x squared. So in this case, a is equal to 1. But if I have a squared minus x, so some other number besides 1, what I'm going to get is the inverse sine of x divided by a plus c. Okay, you'll want that generic one because sometimes it pops up like on final exams. All right, let's do our tangent. So 1 over 1 plus x squared dx. Right, this should look like, what's that? That's a derivative of our inverse tangent, right? If I take the derivative of inverse tangent, I get this. If I take the derivative of inverse sine, I get that. So if I were to integrate this derivative, that's what I'm getting. It's important to recognize, because often these inverse trig functions show up, you know, unexpectedly. All right, let's do a generic solution for it. So 1 over, instead of 1, a squared plus x squared dx. Okay, and that's going to equal to 1 over a inverse tangent of x over a, and then don't forget the plus c. Your generic solution. Like I said, they pop up. All right, my lecture examples. Example number 3 has a trick solution on it, and I think this has a trick solution. And I think, I can't remember if you've got this on like a homework problem. These things kind of pop up every now and then too. You need to know how to manipulate stuff. So I've got 7z squared plus 5 all over z squared plus 1. I'm integrating with respect to z. I'm almost, look, z squared plus 1, that kind of reminds me of an inverse tangent function, right? But this numerator is kind of like messing me up. I can't do anything with that. So I need to rewrite, I have to rewrite my equation. I'm not changing anything. I'm just rewriting it, right? So I'm going to take my 7z squared. That's the term that's messing me up. So 7z squared, right? And I'm going to rewrite 7z squared as 7 times z squared plus 1 minus 7. Let's think about that one for a minute. If I were to distribute, I'm going to get 7z squared plus 7 minus 7. right? So the 7's would cancel and I'd just be left with 7z squared. So now I'm going to substitute this whole thing for that, right? Let's see what we get. So it's going to look like 7 times z squared plus 1 minus 7, now plus 5. Z squared plus 1 dz, and we're going to take the antiderivative. So let's clean it up a little bit. So this is 7 z squared plus 1. This minus 7 plus 5 is minus 2. Okay. Now watch what I'm going to do. This is part of your toolkit. You're learning how to do this stuff. I have a single term in my denominator. That's why I started writing it with parentheses. I'm going to break this up into linearity. I've got this term plus this term, or minus this term here. Okay, so I'll have two functions, right? And so instead of finding a common denominator and bringing it together, I'm breaking my functions apart, my fractions apart. So this is going to look like 7 z squared plus 1 all over z squared plus 1 dz, taking the integral, minus 2 all over z squared plus 1 dz. Now these will cancel, right? Let's rewrite this. I'm going to bring the 2 out. I'm going to cancel that. So it's going to be equal to the integral of 7 dz minus 2 1 over z squared plus 1 dz. I could bring the 7 outside the integral too. It doesn't matter. So when I integrate this, I'm going to get 7 times z minus 2. This looks like my inverse tangent, right? Minus 1 of z. Don't forget your plus c. You don't want to go through all that nice work and then forget your plus c and I have to take off a point. And we do on the final exam. If you forget your plus c, you lose 1 point. It's a painful thing because you're doing everything right, but you forgot your plus c and we have to take off a point. Okay. All right. We're going to learn how to handle that one. All right. So there's a process called integration by substitution. And for that, we need to remember our chain rule. So we're going to do our chain rule in antiderivative form. Right, so remember your chain rule. So the chain rule was like when I had a composed function. F was composed of g of x, and I needed to take that derivative. So I took a derivative of the outside function, and then I had to nest down in for all the derivatives on the inside. And what I said was, oh, substitute. So u equals g of x, du equals g prime of x, you know, dx, right? And then I can substitute. So this just becomes f of u, and I'm taking that derivative. And then I substitute back to get my answer. Okay, so now we have a theorem. We're going to use this idea. It's called integration by substitution. Integration by substitution. So first off, we need to say f and g are differentiable. Oops, I'm running out of space. Differentiable are differentiable functions. Okay, so now what I have is I'm dealing with f prime of g of x times g prime of x dx. Look, it's handed to you, right, in that format. The trick is when you're looking at this as an integral, the trick is to recognize which is the derivative and which is the nested function. Okay, that's part of what we're going to be learning. So I can do my substitution is going to be, I take my inside function, typically it's usually a more complicated function, u equals g of x, and I take that derivative, g of x dx. And now what I'm going to do is I'm going to substitute, sorry, that's g prime of x dx. So I'm going to substitute g prime of x dx for du. I'm going to substitute g of x for u. So now what I get is f prime of u du. And then what I get is f of u plus c. And then I have to substitute back right? Back, so it's in terms of x. So it's going to be f, right, of g of x, you know, times, all right, I'm going to get this here, f of g of x plus c. Okay. Okay, guys. We'll do an example, and then I'll stop and answer questions about the homework. Okay, so example 4, cosine of e to the x plus 7 times e to the x dx. Now, you're going to be in a situation where you've got multiple functions that you need to integrate, right? So I've got a function here, and I have a function here. We're going to be learning tools to integrate multiple functions, okay? But the trick is first to ask yourself, you have to go through a checklist of easiest method first, most simple method first. The first method is, can I just integrate it normally? And the answer is no, because I've got multiple functions here that I'm dealing with, okay? So now my second question is, right, can I do substitution? So which function am I going to use to substitute? Well, usually the function that's nested is the one I'm going to substitute. U equals e to the x plus 7. So I need to take my derivative, is e to the x dx. Don't forget your dx part. Look, e to the x dx, that's my du. So I can rewrite this as cosine of u times du. I substituted in for u, and I substituted in for e to the x dx. Right, when I integrate that, I'm going to get sine of u plus c. And then I'm going to substitute back. Don't forget to substitute back. Okay, back in for u. So I'm going to get sine of u, e to the x plus 7. And then plus c is my final answer. Okay. Okay, guys, substitution. When we meet again on Monday, I'm going to do more substitution examples. And then we're going to do part 2 of this chapter where I do another method. We'll talk about what that method is on Monday. Anyway, okay, e to the x plus 7. Okay. All right. Questions about the homework? Anybody have? We have about 5 minutes. I can answer questions. So the quiz today is on chapter 3.5, which you're welcome to ask me about 4.1 as well. Okay, 4.1. 17. All right, so 4.1, chapter 4.1. This is number 17. So it says, give an explicit solution to dA dt equals t a squared, a naught equals 6. So we've got two solutions are possibly a of t equals 0, and then a of t equals 2 over c minus t squared. Okay, this is from our book, sorry. In the chapter in our book, they talk about this like specifically. I think this problem they actually go through. So we're going to solve for c in the second equation, this one right here. Okay, and we're going to discard a of t equals 0 because a of 0 equals 6 doesn't work. So it's kind of an erroneous solution. Okay, it's a trivial solution. This one's trivial. All right, so I'm going to say a of 0 equals 6. So I'm going to go 2 all over c minus 0 squared. So this becomes 2 over c equals 6. So c equals 1/3. Solution is 2 over 1/3 minus t squared, which is, if I clean it up, it's also true I can get it to 6 minus 3t squared. Both of these are fine. However you want to make that work. This is like I said, it's right from our book. And you know, 44 is actually it's a long, it took me a whole page to do. What I'd like to do is I'll scan it in and I'll put it up on our modules page for the homework, okay? So chapter 4.1, question 44. So to post, I'll post that. Okay. Any other questions, especially on 3.5? That's what you guys have your quiz today on. The quiz will open up at noon today. Okay. Okay, guys, have a great day. Have a good weekend. And oh, 3.5, number 5. Okay, really quick. All right. Number 5. Okay, so we've got the limit as x goes to infinity, the ln of x all over radical x. All right, so as x goes to infinity, right, I just do my quick check. I plug it in, I get infinity over infinity, which is indeterminate. So I can use L'Hopital's rule for it. Remember, you have to specify all this stuff out. Okay, so I'm going to go limit as x goes to infinity. I take the derivative of the top, 1 over x. Take the derivative to the bottom, 1/2 x to the minus 1/2. Okay, which, let's clean that up. I get, when I clean that up, I get ultimately 2 radical x all over x. Okay, which when I deal with exponents, right, this is x to the 1, this is x to the 1/2, right, which is the limit is going to be 2 all over radical x. Which means as x goes to infinity, this thing is equal to 0. Okay. Okay, guys, have a great weekend.
Thank you so much.
Take care. Bye.
Thank you.
Thank you.
Thank you.